Now let's begin talking about deduction rules for predicate logic. All of the natural deduction rules that exist in propositional logic also exist in predicate logic. So we're really expanding our repertoire of deduction rules here. First, let's talk about the universal quantifier. For the universal quantifier, we have a couple of deduction rules, one which is relatively straightforward and then one that's more complex. So let's deal with the relatively straightforward one first. Here it is. This is the elimination rule for the universal quantifier. Remember, this is what we use when we're reasoning from a universal statement. So think about it. Well, what should be true? If we know that a universal statement is true, then it should be, or the formula that follows the universal quantifier rather, should be true about anything in the domain of the model. So here's the rule. Suppose we have no variables in the term t that become bound in the substitution of replacing x with t in the formula phi. And we're going to use uh, the, um, the word substitutable for this situation. So we say that t is substitutable for x in this formula. If you think back to some of the work we've done in predicate logic, I think you'll remember examples where we showed in the realm of substitution, or we at least discussed the idea that in some cases substituting a term for a variable might not really make very much sense. Syntactically it might be okay, but if variables in the term, or say if the term is just a single variable all by itself, if that becomes bound when we substitute it, then the meaning changes in pretty much any situation. So we don't want to allow that situation. We want t to be substitutable for x in the formula, so that basically t is just an instance or represents an instance of the variable. Then the following deduction is allowed. So suppose we're going along in our proof and we already have for all x phi. Well, then it's okay to deduce phi with x replaced by t. Essentially, we're just applying the universal formula to a particular instance. This is something that's sometimes called instantiation, because we're taking a universal statement, something that should be true for anything in the model, and we're saying, okay, well, if I've got a particular object that's named by this term, then certainly the statement ought to be true about that particular object. Here's the more complicated rule. This is the introduction rule for the universal quantifier. The idea here, before we get into this, the syntactic details of this deduction rule, is how do you prove a universal statement? Well, informally in mathematics, the way we usually do this is to say, well, let x be an arbitrary real number. Then I reason for a while and deduce something about x. Since x was arbitrary, then I can say that the formula or the result that I've proved should hold for any real number x, or whatever the situation might be. Here's the way we're going to do this formula. We prove a universal statement or assertion about a variable x by showing that it's true about a new constant symbol called a parameter, about which we've made no prior assumptions in the proof. So briefly, let me try to explain why do we need this. What we're doing here is trying to formalize the idea that we need to introduce a new name for the arbitrary object that we're going to reason about. If somehow the name that we've chosen or the variable or constant symbol already appeared in the proof, we could be in trouble. Let me show you how that works. Suppose I try a very simple proof here. I'm going to start with the assumption px. So p is a one-place parameter. So that's an assumption for my proof. And then suppose we didn't have this restriction about using parameters. So suppose I said, okay, well, I've just proved something about x. What if I allowed myself to deduce for all x px from that? So notice I'm not following the rules here. I want to show you why we would get into trouble if we allowed this. This is a conditional subproof, or it allows me to prove an implication, which would be px implies for all x px. Notice what I've done here is to generalize or apply the universal quantifier to a variable about which I actually do have a very specific assumption, namely that x is in the interpretation of the predicate p. And notice this formula, if you think about it, is not valid. Not valid. It's probably not hard to see that. Just to explain, here we do have the free variable x that appears toward the beginning of the formula, but this would tell us, I mean, if this is going to be valid, then it should be true in any model under any assignment of the variables. In particular, if I can simply pick one object in the domain that satisfies P and assign x to that variable, or assign x to that object, then the formula for all xp of x would have to be true in that model. So in other words, this would basically say whenever P has at least one object which satisfies it, then all the objects in the domain must satisfy it. Clearly that's not true. It's very easy to come up with examples where that wouldn't work. So that's just one example showing why we need this idea of a parameter. Okay, here's the way the formula or the rule works. Suppose C is a parameter, that is a constant symbol that doesn't occur in the language under discussion, and it doesn't appear in the main line of proof containing the subproof that I'm about to write below. Then we can do the following. So imagine our proof is going on. Now we'd like to prove a universal statement. We're going to do this new sort of subproof, which doesn't actually have an assumption, but mentions the new constant C. So here's my new constant C. And I'm going to say, suppose I'm able to go down here and eventually prove phi with x replaced by C. So notice, here's my subproof, and anywhere outside that subproof, the new constant C shouldn't appear at all. So that makes it very clear. I mean, the way this proof system is set up, we've taken great lengths, or we've gone to great lengths to ensure that there's no way that there could be some hidden assumption about C that would allow us to prove something false. So if we're able to do this, then it should be safe to conclude for all x phi. That is, we've proved that the statement phi is true, or the formula phi is true, about an arbitrary object. If we can do that, then it makes sense to allow ourselves to do this deduction. Okay, if you think about how the existential quantifier is related to the universal quantifier, then, I mean, in a sense, we could always get away with simply recasting any existential quantifier as a universal quantifier. But let's actually talk about rules for this particular quantifier. Here also we have one relatively straightforward one and one more complex one. The situation is reversed because of the way that these quantifiers relate to each other. So for the introduction rule for the existential quantifier, we would say, suppose there are no variables in t that become bound in the substitution where phi with x replaced by t, again, that's saying that t is substitutable for x in this formula. Then in this case, what makes sense? I mean, think about what's happening here. If we've actually proved that an object exists that satisfies phi, then it certainly should be safe to say the more general statement that such an object exists. In other words, if I go along and I've proved phi with x replaced by the term t, then certainly it should be okay to deduce exists x phi. So that's the introduction rule for the existential quantifier. Now let's talk about the more complicated elimination rule. So here, the idea is, suppose we've proved an existential statement and we'd like to reason from that. Well, again, it's useful to think about our experience maybe in other areas of mathematics, reasoning in this way. Suppose we know there is an object that has some property, then usually we would say, well, let A be an example of such an object, and then we would reason about A. Now, in that situation, it's very important, even in an informal reasoning, to be sure that the object or the name that we've chosen has not been used previously in the proof, or at least there aren't any active assumptions about that name. So here's the rule, and this is very similar to the introduction rule for the universal quantifier. Suppose C is a parameter, again a constant symbol not occurring in the basic language that we're using, that doesn't appear in the main line of proof in the subproof that I'm about to write. Then the following is allowed. So what do we have here? The situation here is a little bit different. We're assuming we have exists x phi already proved. Now we'd like to reason from that. Well, again, we're going to have an assumption here that uses the new constant symbol c, but here we actually do have an assumption. So the assumption is phi with x replaced by c. So that is, we're saying, well, suppose C is such an object. We know that there exists an object that has a certain property. Suppose C is such an object. And then we go through some steps here, and we prove a conclusion within the subproof psi. I want to explain a little bit about what's going on here. We have to be a little bit cautious here because what I'd like to say now is it's okay for me to deduce psi outside of the subproof. Of course, if I'm going to follow this rule, the fact that C shouldn't appear outside the proof, then the conclusion I draw can't have to do with that particular new constant symbol. So that's an important little detail that we have to remember or have to be aware of here. So the idea is we're saying suppose C is an example of an object with this property. I do some steps of reasoning and get some kind of conclusion. If the conclusion doesn't talk about C, then it should make sense to say, well, psi just follows then from the original existential statement. This subproof is just explaining how that comes about. Okay, we'll see some examples of all these rules in the next lecture, but let me just introduce a couple more and then we'll be done with laying out the rules for natural deduction for predicate logic. And these are rules for identity. Fortunately, these are relatively straightforward. The first one is very much straightforward. So given any term of the language, we can introduce the formula t equals t at any point in the proof. So in other words, it's always okay to introduce an equation if both sides of the equation are exactly the same syntactically, because it certainly makes sense that those then should have to refer to the same object. The elimination rule for identity is a little bit more complicated, but it's similar to some of the things we've already seen in this lecture. In this case, suppose phi prime is obtained from phi by substituting the term t2 for some occurrences, maybe not all, of t1. t1 is in phi. We have to assume that t1 doesn't contain any bound variables because otherwise the substitution isn't really feasible, even syntactically. And also so that t2 is basically substitutable for t1 in all, at least in all those particular occurrences. So no variables in t2 become bound. Then the following is allowed. So we're going along in our proof and we've proved either t1 equals t2, or I'm going to use a slash in the way that we've done this in the past, or t2 equals t1. So we could have either one of those as our prior step in the proof. The idea is if we've already proved phi, then it's perfectly okay to substitute t2 for t1, again, assuming that the term is substitutable and assuming that we're substituting into a term that actually makes sense. Then we're allowed to deduce phi prime. So those are the rules for natural deduction when it comes to predicate logic. Again, notice we just have an introduction and elimination rule for each of the two quantifiers, and we have an introduction and elimination rule for identity. So 6 new rules, but you can keep them organized in your mind if you think of them in that way. And we'll see some examples in the next lecture.